So last part of the course, last big chapter, it's sequences and series. So first, a big definition. What is a sequence? So a sequence is a function whose domain, let's call it F, whose domain, you know what the domain is n, okay? N being the natural numbers. So what's n? So some include the zero, some don't, okay? So let's go 1, 2, 3, 4, all the way, okay? So the domain is n, means that F takes its values from only integers, positive integers. Okay, that's what a sequence is. So for example, if I'm telling you F goes from, so this is a new notation for you, okay? It goes from R to R, and to each X, it associates, let's say, 1 over X, okay? So this is a more extensive way of writing a function, okay? This is the same thing as writing what we've learned all our lives, F of X is equal to 1 over X, okay? That's writing the same thing, okay? Except that when we write it this way here, I'm also specifying where does the X come from. And here I'm specifying that the X is a real number. Okay, so that's the regular function. If I want a sequence, well, the sequence would be like this, n, so it's not R anymore, it's from n until R, and for every number, so I'm not going to call it X anymore, I'm going to call it n, because just to show that it's an integer, to n, it associates 1 over n. Okay, and this we write, so either f of n equals 1 over n, or the notation that we use, f of n, we're going to call an, which is the nth term of the sequence. Okay, so I'm going to explain what I just said here. So basically here, well, this function, we all know what it is. Okay, so let's say I'm just going to be interested in positive numbers, okay? So I'm just going to take R plus. R means only the positive values. If I'm to draw the graph of this, okay, well, if X is 1, then it's 1. If X is, let's say, a half, then it's 2, right? If it's a third, then it's 3, and so on. So if I am to draw the graph of this function, it will look something like this. Okay, but this one here is different. Let's call this n. Because now I'm only interested in integers. So there's no, n cannot be 1/2, n cannot be 2/3, okay? N can only be 1. So if it's 1, it's so 1, 1. 2, it will be 1/2, 3, 1/3, and so on, and so on, and so on. Okay, so there's a difference. Here it's continuous, here is what we call discrete. Okay, you could count them. Okay, and you could write actually all the terms of your sequence. So you could write it like this. So when n is 1, it's 1. When n is 2, it's 2. It's 1/2, 1/3, 1/4, and so on forever. Okay, in this case, this is 1, 2, 3, 4, and so on. Okay, and this will be 1, 1/2, 1/3, 1/4. Okay, that's what a sequence is.
Okay.
Okay, if I am to give you a little more definitions here, so the sequence AN equals 1, 1/2, 1/3, 1/4, 1/5, and so on. Okay, so all these are called terms. Okay, so this is called the first term, so we're going to call it A1, second term A2, A3, A4, A5, and of course the nth term will be just 1 over n. Okay, and it continues forever, doesn't stop. Okay, and all these are called, they're called terms of my sequence. Any questions? Okay, so let's do one little example. Okay, one first little challenge that you could have. Find the general term of the sequence so let's do number 1. So I'm going to give you some terms, and you have to tell me what the general term is, okay? So let's say, I'm going to start with a very easy one. So 1, 2, 4, 8, 16, 32, and so on. Here's one. Second one, a little more complicated. Let's say, 1/2, 2/3, 3/4, 4/5, and so on. And number 3, let's say, -3 over, so -3. Okay, first one was -3. Okay, I'm just inventing it right away on the fly. Let's say 9 over 4. Let's say -27 over 9. 81 over 16, and -243 over 25, and so on. Okay, so here are 3 sequences. I want you guys to find the general term. In other words, AN equals what? What's the nth term of this sequence? What will it be? Can you tell me what that is?
Is it 2 to the power of n?
Very good. 2 to the power of n, but you have to specify that n starts at 0 in this case, because 2 power 0 is 1. Okay? Or if you want to start it at 1, then you have to do 2 power n minus 1, because the first term has to be 1. Okay, so we're going to write it like this, with n greater or equal than 0. Okay, if you want. Okay, or you could write it like this. Okay, whatever you want. Okay, depending on the book, there's different ways to write it. We're just going to write it like this. Okay, with n greater or equal than 0. So it's starting at 0. This one here. Okay, so this exercise is basically just pattern recognition. Okay, recognize the pattern. Can you tell me what that is here?
Is it n over n plus 1?
What? What did you say?
N over n plus 1?
Yeah, this is n over n plus 1. And n starts at 1 here. Okay, the first term, you plug in 1, you get 1 over 2, here it is. Second term, n equals 2, you get 2 over 3, here it is, and so on. So this basically generates all the terms here. Good? This one here is a little more complicated. Yeah, tell me.
For the last one, could you also say n plus 1 over n plus 2 starts at 0?
What did you say? N plus 1? Yeah, n plus 1 over n plus 2, and you can start at 0. Yeah, perfect.
All right, okay.
Good. Same thing, okay? Or n plus 2 over n plus 3, and you start at minus 1. Or n minus 1 over n, and you start at 2. Okay, you could, whatever you want, okay?
All right, okay.
We don't want to start at negative, so forget the second to last that I said. But you could do n minus 1 over n and start it at 2. That will work. This one here is a bit more complicated.
Is it like
tell me?
minus 3 to the power of n over perfect squares, but I don't know how to like write perfect squares.
Okay.
Divided by n to the 2?
Okay, that's very good. So it's negative 3 to the power of n. That's good, because when I start at 1, it's minus 3. At 2, it's 9. At 3, it's minus 27. At 4 is 81, and so on. So this takes care of the numerator. And the denominator is basically just 1, 4, 9, 16, 25, which is perfect squares. So it's n squared. Okay. And of course, n starts at 1. Any questions? Okay, that's the first thing that you're going to have, first exercise that you'll be asked to do on the worksheet, is to recognize a pattern and identify what the general term of the sequence is. Okay, and that's very important, because you'll see when we're going to do Maclaurin series and Taylor polynomials, you might have sometimes to do this a bit more complicated with series, but to find a general term. Okay, you will see. Okay, and it ends up being the same exercise.
Sir?
Yeah.
Is there a formula to use to find like this type of things?
A formula?
Yeah.
No, there's no formula.
Okay.
You have to just recognize the pattern. So you just have to use your judgment and try to recognize. So 3 times 3 times 3 times 3 times 3. Oh, so it seems that the base is 3. Minus, plus, minus, plus, minus. Oh, it seems that there's a minus power n. Alternate signs. Oh, the denominator is perfect squares, perfect square. That's it. You just have to, and sometimes it's not very easy. I'm just telling you. Okay, these are 3 easy ones. Okay, in the worksheet, I think they're okay, but you're gonna have to think a bit more. Okay, so now comes the more difficult thing that I have to show you. Okay, and it's a real big concept. Okay, so you have to make sure that you understand what I'm going to say now. Okay, because we're going to deal with this for the rest of the course now. Okay, just understanding the concept. I'm not going to go into details on calculating what I'm going to show you, but just understanding what it means. Okay, so here we go. a sequence AN. Okay, so a sequence AN. So very important word here, converges. To a limit, let's call it L, if and only if. Okay, so if with two F's means if and only if you've never seen this before. If and only if. Okay, I'm going to explain what that means. So listen to this big definition. It's going to look weird, but I'm going to translate everything. For any epsilon that is greater than 0, there exists a big N natural number N, a big natural number N, such that whenever N is greater than big N, then the difference between AN and L is less than epsilon. Okay, so I'm sure you didn't understand anything, but I'm going to translate this in English in 2 seconds. Okay, but this is a very, very important definition. This is a definition of convergence. And the only thing I'm expecting from you out of this definition is that you understand what it means. Okay, there's calculations to show that a sequence converges using this definition. I'm not going to ask you this, even though it's on the worksheet. If you want to try it, you're welcome. But I just want you to understand the concept and what this means. And so for this, you have to concentrate now. Okay, so first, the vocabulary. Okay, so what does this symbol, you know what it means? The upside down A.
For all values?
Very good. So for all values, so for any or for all, okay? This E is epsilon. Okay, it's a Greek letter. We usually use it to like to design a not design like identify a small number, a very, very small number. Okay, so epsilon is usually a small number. So for any small number, for any small positive number, okay, that's what it says. For any number epsilon, it's very small. This means there exists a number n, okay, any number n. There exists a natural number, an integer, a positive integer, such that, okay, so the 2 dots I just say for such that, whenever small n is bigger than that number, the difference between the nth term and the limit is smaller than epsilon, smaller than the small number that I wanted. Okay, so I'm not expecting you to get it right away.
Sir?
Yeah.
Epsilon just means a really small number.
Yeah. Okay. It's really any number, but we usually use it for small numbers. You'll see, you've probably seen this in maybe chemistry or physics. You've probably seen this epsilon sometime. Okay. or sometimes they use a delta x or something like that, okay, or delta t, or I don't know. Okay, but it's something very, very small.
Master,
Yeah.
when you say the limit of what?
What? Converges to a limit.
Oh,
What do
okay.
you mean the limit of what? It
Oh, no.
converges to a value L, which I call the limit. Just like in calculus 1. When you did the limit of a function, okay? So in calculus 1, there is also a definition like this, an equivalent one, okay? And like a similar one. I know when I taught it last semester, I didn't teach it. I used to teach it before, but students were lost, okay? Because this concept is a bit difficult to grasp. I'm gonna try my best, but you guys are in calculus 2 now, so I'm guessing you're a bit more, like you've seen limits, and so you have a little more maturity to understand what convergence means. And there's no choice, because from now till the end of the course, we're only going to deal with convergence. Okay, so you really have to understand what convergent means. Okay, so I'll take my time. So again, and then I'm going to do an example with an actual sequence, and you will apply and understand what this means. But first, let's stay a bit on the theory side. Okay, so again, if for any number, any small number, okay, no matter how small I want, I could find a number n such that whenever n is bigger than that, the nth term is close enough to L. Okay, it's closer to L than epsilon, right? It's smaller, the distance between the nth term and L is smaller than epsilon. Then we could say that this sequence converges to L. Okay, let's go to an example. Okay, 2 seconds. And then I'm going to come back and re-explain the definition. Okay, so for example, the sequence that we did before, which is an is 1 over n, okay, with n greater or equal than 0. Well, it seems to me that, well, this sequence is what? 1, 1/2, 1/3, and so on and so on. It goes on forever, right? There's an infinite amount of terms here. Do you think that it converges to something? Anybody?
To 0?
Yeah. Okay. It seems to get closer and closer and closer to 0. Okay. The further I go in the sequence, the closer I am to 0. Okay. So this is pretty obvious, because I'm going to write this. An seems to converge to 0. Okay, pretty obvious. Few reasons. First of all, since if I do the limit as n approaches infinity of 1 over n, right? As n approaches infinity, right, of that term, well, that's a very, very easy limit that you did in calculus 1. 1 over infinity, that's 0, period. Okay? It's simple. It's a limit, a very simple limit to evaluate. And most of the time, you will find limits or of sequences or determine if they converge or diverge using what you did in calculus 1, which is evaluating limits at infinity. Okay. The only thing is that since now it's discrete, you might have some things that are a bit different. Okay. You might have to use the squeeze theorem a bit more, but okay. But most of the time, you could find if a sequence converges using this limit, and that's what we're going to do. Okay, I'm not going to ask you to do it using this, but the concept is what? Why could I say that this sequence converges to 0? Okay, using this definition, Because look at this. This is my sequence. 1, 1/2, 1/3, 1/4, 1/5, 1/6, right? This is my sequence. 1/7, so on and so on and so on and so on. And somewhere here, it's getting, there's my limit, 0, which of course I will never reach. Okay, you will never reach 0, right? This could never be equal to 0, as you know. Whatever the number you put here, you will get 0.0000000000000 something, 1 somewhere, okay? But you'll never reach 0. But what this tells me is that if, let's say I choose epsilon to be whatever I want. Let's say 0.0000001. Let's say that's my epsilon. Okay. Well, there exists a number n. There is a point in time where my sequence for sure will enter here. I could get to this very easy. I just have to take n equals to 10 billion. If I take n equals 10 billion, I'm going to land inside here. My term will be inside. And then after that, every term will be in here. Okay, so if I want it to be within 0.0000001 of my limit, yeah, well, there exists a corresponding, and there is an n. There is a value that will make all my terms inside that interval. And that's for any, very important, for all epsilon. Let's say you want to be even more precise, no problem. You want to be more precise, we'll just increase the n, and this will be smaller, perfect. And then you'll have to get more terms to reach inside, no problem. So this is another way of saying that you could get as close as you want to the limit. Okay.
Sir?
Yeah.
How do you choose your epsilon?
You don't choose it. You don't choose it. I'm just saying is if no matter what the epsilon is, I could find an n that will have all the terms within epsilon of the limit beyond that n, then it converges. That's what's a bit tricky, because it's the for all epsilon. It means that no matter how close, for any precision. Okay, it's like if okay, I'm gonna have to raise. Okay, just any questions on this, and I'm gonna give you an example so that you visualize.
Sir.
Yeah.
The orange vertical lines you drew here, would that represent the big N?
The orange lines here?
Yeah. Would that?
No, this tells me the distance from the limit, how close I want to be. The n is the nth term. So this is the 7th, 6th, right? 5th term, so. This I have the 1000th term, and go on. Here I have the 10th to the 8th term, and then here I have 10th to the 20th term. I'm inside. Understand?
Yeah.
Okay. Okay, so just to visualize what I just explained, imagine this. Okay, so I'm here. That's me. Okay, typical example. Okay, and here there is a wall. Okay, typical example. And every step, every time I do half the distance. Okay, classic. Okay, so let's say this is 2 meters. I'm going to jump 1 meter. I'm going to end up here, half the distance. Okay, that's my first step. Second step, I do half the distance again. Second step. Third step, I do half the distance again. and half the distance. And half, and half, and half. You with me? That's what I'm doing. Okay, so the question is, of course, am I ever going to touch the wall?
Yes.
Yes. How am I going to touch the wall? Who said yes?
Me.
Yeah, you're going to touch the wall?
Yeah.
How?
Wasn't it proven that 1/2 plus 1/4 plus 1/6 is equal to 1 at the end?
No. Who proved that?
Yeah. No?
It's equal to?
It approaches 1.
Ah, okay. I'm not arguing with you that I'm approaching the wall. I agree with you. But am I going to touch the wall? When am I going to touch it? Tell me when. Okay, I'm going to touch it. When? After how many steps do I touch the wall?
Infinite amount of steps.
Oh, I don't live that long. Okay, nobody lives that long. Okay, so it doesn't. Infinity, of course, in infinity you could do crazy things, but in real life or in real, using real numbers, you're never going to touch the wall. Okay, but okay, you all agree with this? That I'm not touching the wall. But let's say I want to be within 1 millimeter of the wall. Could I get there that close? Can I get within 1 millimeter of the wall or not?
Yeah.
Yeah. Can I get within 0.00000001 millimeter of the wall? I could. No problem. I just need to do a lot of steps. Maybe it's going to take me 10 years, jumping until I get within 0.0001 millimeter of the wall, but I'm going to get there. And after that, all the steps are within 0.0001 millimeter of the wall. That means that I could get as close as I want to the wall. That means that I'm approaching my limit as my number of steps goes to infinity. The limit is the wall. That's what it means. Okay, and that's the definition that I just wrote before. For any epsilon, so for any 0.001 millimeter closeness to the wall that I want to be, there exists a big N, so there exists a number of steps that will guarantee that I fall within that precision of the wall, within that closeness to the wall, within that epsilon. Is it better now, the definition?
Yeah.
Okay. So, example. Evaluate the following limits. Okay, if they exist, of course. First, so limit as n approaches infinity of n squared plus 1 over 3n squared plus 5. Second, limit as n approaches infinity, sine of n over n squared. Yeah, so this basically is just a review of calculus 1. So the first one, of course, it's infinity over infinity. So we could use, what can we use?
Lopita.
Very nice. So let's use L'Hopital's rule. limit as n approaches infinity. So the derivative of the top is 2n over the derivative of the bottom, which is 6n. If you simplify the n's, you get 1/3. Okay, so in other words, if you start writing all the terms of this sequence, let's write a few of these terms. Okay, so this is basically if you plug in 1, so it's 2 over 8. Second term, when it's 2, you get 4, you get 5 over 17. Then when it's 3, you get 10 over 32. And it keeps going like this. And you see it seems to get closer and closer to 1/3. Okay, 10 over 32 is almost 1/3 already. Okay, the more you go, the closer it gets to 1/3. Good. And you could do it. I'm not really expecting you to find all the terms, although it's a good exercise. But that's what you're going to be asked to do, is to evaluate the limit, and that's very simple for now. Here, what do you have? What do I do here?
Also Lopita.
No, because now it's not infinity over infinity. Because as you see, sine of infinity, I don't know what that is. It's not, that's not infinity. And the bottom is infinity. What do I use here? We did this in calculus 1, I remember. I mean, for those who were with me, and you probably did it with your other teacher for sure. What do we do? Okay, you guys are rusty. So sine of n is definitely between -1 and 1. That's for sure. True? Right, the sine is always between -1 and 1. And so if I divide by n squared, still true, still holds. Okay, so sine n over n2 is between -1 over n2 and 1 over n2 always. And so if I take the limit on each side, so limit as n approaches infinity, still true. And that's a very easy limit. -1 over infinity is 0. This is an also very easy limit. 1 over infinity is 0. So this limit is between 0 and 0. And so the limit as n approaches infinity, sine n over n2 is 0. Any questions? How do we call what we just used?
Intermediate.
Squeeze theorem.
Squeeze theorem. I think.
What?
The squeeze theorem. I think.
Okay. No intermediate value theorem here. Okay, that's not the intermediate value theorem. That's a squeeze theorem. Okay, squeeze theorem. Okay, or in French, le théorème du sandwich, or critère de D'Alembert. That's the guy who I think invented this. Okay, you just squeeze your term between two terms that I know that approach a certain same value. Okay, any questions? Okay, so the rest is just exactly like calculus 1. So evaluating limit using either L'Hopital's rule, squeeze theorem. So let me give you one tougher one. Okay. I just want to make sure that you'll be able to manage on your own when you do the examples. So let's do number 3. Let me give you a tough one now. Time is it? Okay, let me do a tough one now. So limit as n approaches infinity, let's say 2 to the power of n over n factorial. Okay, so have you ever seen what the factorial means? Who has never seen this? You've all seen it?
I've never seen it.
Okay, so you've never seen it. I'm going to explain what that means. Okay, so this is called, we read it as n factorial. Okay, and n factorial is what? Is equal to just 1 times 2 times 3 times 4 times 5 all the way until n. That's what n factorial means. Okay, so for example, I don't know, 4 factorial is 1 times 2 times 3 times 4, which is 24. Okay, and the 5 factorial will be until 5 will be 120 and so on. Good. Just for you to know, one thing is that 0 factorial is 1. Why is this true? It's not for this course. Okay. So we're looking now for this limit. Now this is much more complicated because I have infinity, all right? 2 power infinity, of course, is infinity, and infinity factorial, which is 1 times 2 times 3 times 4 times 5 until infinity. Of course, you get infinity, top and bottom. So I have infinity over infinity, but the bottom, I have no idea how to, if I wanted to do Lopita's rule, I don't know how to derive this. Questions? Okay. So let's try this. So 2 power n over n factorial is definitely positive. Okay. 2 power anything is a positive number, and n factorial is a positive number. Plus over plus is plus. So this is, could never be less than 0. Impossible. And 2 power n is basically just 2 times 2 times 2 times 2 times 2 dot 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 times 2 times 2 n times. That's what it means. And on the bottom, n factorial 1 times 2 times 3 times 4 times 5 dot 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 times, well, n minus 1 times n. Are you okay with this? No questions, so I'm guess you guys are okay. Kitya, you okay? Yeah? Liam? Yeah?
Could you please explain how you got the first part? The top, yeah, the top.
The top?
Yeah,
2 power n
yeah,
is 2 times 2 times 2 times 2 times, that's what exponent means, right? If I have 2 power 5, it will be 2 times 2 times 2 times 2 times 2.
okay.
Okay, so 2 power n is 2 times 2 times 2 n times. The only thing is I don't know what n is.
Okay.
So I just multiply 2 by itself n times. Gaetano, you're good? Okay.
Isn't the answer infinity? Because if you use Hopital's rule,
No, I can't use Lopita's rule. How will you derive the bottom? How did you
It would-
derive? What?
well, isn't like an n factorial something multiplied by n? or like n multiplied n times. Unless that makes it a number, in which case it becomes 0. And then we have
No,
some
no,
funky stuff.
it's more complicated than that.
Okay.
Okay, so 2 power n over n factorial is equal to this for sure. Now what I'm going to do, okay, that's tricky and we're a bit short on time. Okay, I'm going to, worst case, I'll redo it tomorrow, but look at what I'm going to do here. I'm going to take these guys here. And what do I have? 2 over 3, 2 over 4, 2 over 5, 2 over 6, and so on, 2 over n minus 1. All these fractions are smaller than 1. So this whole orange term here is definitely less than or equal to 1. Guaranteed. Okay, it's all, I'm multiplying fractions that are smaller than 1. So if I multiply 2/3 by 2/4, I'm going to get 4 over 12, which is still smaller than 1. And if I multiply by 2/5, even smaller, even smaller. I'm just getting smaller and smaller numbers. So these numbers are smaller than 1. Guaranteed. This number here, this product is less than 1. Okay, so what do I have? 2 times, well, this is out. And this is 2 over n. And if instead of writing this big orange thing, I write 1, then I'm going to get something bigger. Because 1 is bigger than this orange thing. Okay? I know it's confusing. And I'm going to redo it slowly next class. Okay? So what I have is 0 is less than or equal to 2 power n over n factorial, which is smaller than or equal to 4 over n. For sure. And now if I take the limit as n approaches infinity of all 3 sides, so limit n approaches infinity, limit n approaches infinity, well, this is 0. Of course, this is 0. So my limit as n approaches infinity of 2 power n over n factorial is equal to 0. So this sequence converges to 0. Okay, it's good to write down the terms. So 2 over 1, then 4 over 2 factorial, which is 2, then 8 over 3 factorial, which is 6, then 16 over 4 factorial, which is 24, then 32 over 120, and so on and so on. And this sequence, if you keep going, it gets closer and closer and closer to 0. You could get as close to 0 as you want. Okay, if you want to say it in a more precise way.